Okay, 19.7 is really the culmination of all of these equations that we've been learning up until now. We'll derive and build up to what's called the Nernst equation. But first of all, let's motivate why we want to do this. Most of the time when we're building practical electrochemical cells, we're going to have concentrations that are non-standard. That is, we'll want some concentrations to be higher than 1 molar, some to be lower than 1 molar for practical reasons. And it would be nice if we could calculate what the actual cell potential is for these cells under non-standard conditions. So the relationship between E and delta G actually gives us the foothold that we need to solve this sort of a problem. So up here we've got the Gibbs energy under any conditions is equal to negative NFE, and then under standard conditions we just add the knots there. But you may remember we also have this equation, that delta G is equal to delta G naught, plus, I wanted to make sure I got that right, plus RT times the natural log of Q. Q is the reaction quotient. Well, let's just plug this in here. So negative NFE is equal to, we'll plug that right there, negative NFE naught plus RT ln of Q. So we've replaced the Gibbs energy under non-standard and standard conditions with the appropriate relationship involving cell potentials. And we can clean this up a little bit just by dividing negative NF from both sides. And so E, the potential under non-standard conditions, is going to equal E naught, the standard cell potential, plus RT over NF times the natural log of Q. This R is the 8.314. T must be in Kelvin. N, again, is the number of electrons transferred in a cell. F is Faraday's constant, 96,485 coulombs per mole. And this is called the Nernst equation. Now, you can apply the Nernst equation to a complete cell, like we're about to do, but I want to point out you can also apply the Nernst equation to a half cell. If you look at the table of reduction potentials for half cells, then those are standard reduction potentials. In fact, maybe it's worth pulling that up. Or maybe not. It's quite a ways back, I think. Sorry, I like to have these figures prepared ahead of time, but I just thought on the spot that it might be worth showing you what I mean. Where are we? There we go. Okay. You can't see it yet, sorry. And let me pull it up again. There we go. Oops. That's not right. That's what we want. Okay, so all of these standard reduction potentials are only applicable under standard conditions. If you wanted to find the voltage of a half cell under non-standard conditions, then you would just look at the number of electrons that are required to perform that reduction. Q for all of these reductions is going to be, I guess I shouldn't say all of them, but Q is always the concentration of products over the concentration of reactants raised to their stoichiometric coefficients. So for most of these, that would be 1 over the concentration of the cation, but you'll notice some of them involve ions on both sides. Some of them are the reduction to an anion, and so just be careful about formulating Q properly. And you can find out the E for your half cell. But I think what I wanted to do is to just go ahead and apply the Nernst equation to a complete cell. So here we are again with the zinc copper 2+ cell that we've been working with. Let's just remind ourselves about what that equation is. We're going to have zinc solid plus Cu2+ aqueous, and that is going to form Zn2+ aqueous plus Cu solid. And so Q in this case would be equal to the zinc 2+ concentration over the Cu2+ concentration. So you can see in that practice problem, let's suppose we have a zinc concentration of 0.00500 molar and a copper concentration of 3.00 molar. So I chose those specifically to have a higher concentration of the reactant, a lower concentration of the product. This will have the effect of boosting the cell potential. We're going to try to improve the standard zinc copper 2+ cell to have a higher voltage. Let's figure out what its potential would be. E is equal to E naught, which is that now very familiar 1.10 volts, plus 8.314 joules per mole Kelvin. And again, I didn't list it in my notes, but we're just going to assume room temperature, 298 Kelvin. And I should point out, changing the temperature here is not trivial. You might think you can just change the temperature and get a new value for T in this equation. But changing the temperature would also affect E naught. Because E naught is related to K and K is temperature dependent, you can see how it gets complicated. Okay, so the E naughts that are in our standard reduction potentials, ooh, I should double check that. Where are we? You know, it doesn't mention a temperature here. I suppose it's possible I should be running these problems at 273 Kelvin or standard temperature. Anyway, we'll just run with it because 25 degrees won't make that big of a difference. But I just want to point out that it's not trivial to change the temperature. You would need to get new values of E naught. Okay, N is 2. And the Faraday's constant is 96,485, what is that, coulombs per mole. And then we'll have the natural log of that 0.00500 over 3. And this is going to end up improving our cell potential a little bit. E is going to equal 1.10 volts plus 0.08 volts to give us finally 1.18 volts. We're not quite done with this section, but I can hear my little girl screaming in the room, so I'm gonna pause this. I think I can do that without splitting it into two. Okay, I think that worked. They're okay. They just needed help with their puzzle on King's Quest, so obviously it was worth interrupting our class for that. All right. The Nernst equation actually raises the possibility of a really interesting type of voltaic cell called a concentration cell. So in a concentration cell, you have anode and cathode half reactions of the exact same type, but they just have different sorts of concentrations. So for example, you could make a concentration cell out of two electrodes that each have copper solid copper rod dipped in a solution of copper sulfate containing copper 2+ ions. The chemical equation in that case would be copper solid, and this would be where the anode is, plus copper 2+ aqueous, and this is where the cathode is. And what's that going to form? Well, the cathode cations are going to be reduced to copper solid. So copper solid cathode. I didn't leave myself enough room here, so it's going to get a bit sloppy, sorry. Plus Cu 2+ aqueous in the anode. So you're oxidizing copper to 2+ ions in the anode, you're reducing 2+ ions to copper in the cathode. Because they're physically separated half cells, this actually works as long as their concentrations are different from one another. Q in this case, then, would be the concentration of copper 2+ in the anode divided by the concentration of copper 2+ in the cathode. Quite an interesting reaction quotient. And E0, the standard cell potential, if everything were 1 molar, then anode and cathode would be identical to each other, and so the potential would be 0. Now we can apply the Nernst equation, where E is equal to E0. In this case, that's a 0, plus, that should be a minus. I was thinking that was wrong. Minus R, 8.314 joules per mole Kelvin. T, again, will have 298 Kelvin. RT over N. For the copper concentration cell, N is again 2. And the Faraday's constant, 96,485 coulombs per mole. And that'll be times the natural log of Q. Let me throw up the practice problem. Right, if we have a concentration cell with our anode concentration of 0.00200 molar and a cathode concentration of 5.50 molar, then we'll actually manage to eke out some voltage from this cell. It won't be much. The voltage is ultimately going to equal 0.102 volts. But interesting that you've got essentially the same reaction occurring in different directions in the cathode and anode. It's the difference in concentrations that are going to cause this cell to give you any potential at all. Ultimately, this cell will run. It will be decreasing the cathode copper 2+ concentration while it increases the copper 2+ anode concentration, and it will run until those two concentrations are equal. That's when the battery will be dead and the potential will drop to 0. Okay, and that's section 19.7.